Welcome to our video on the geometry extremas in the complex plane. First, let's see on part A, the circular locus.
The expression in the modulus represents the distance between a point on Z and Z node. We can substitute in the distance formula to get the circle equation labeled 1. To find the complex numbers satisfying Z minimum and maximum, we must find the equation of line passing through the origin and center of circle obtained from equation 1. Substitute this line equation into the circle equation to find the x and y values of Z minimum and maximum. We can verify our answers by using the formula for Z minimum and maximum. Maximum argument Z is theta node plus alpha, while minimum argument Z is theta node minus alpha. We substitute y equals to mx into the circle equation. We set the discriminant as 0, so the line intersects the circle at one point only, meaning it is tangent to the circle. Next, find the values of m minimum and maximum using the quadratic formula. Because our discriminant is equal to 0, our quadratic formula can be simplified to find the values of x and y for minimum and maximum argument Z.
In GeoGebra, we plug in the values from the calculations. Z1 is the center point of the main circle. Z2 is for determining the radius of the circle. Point A and point B are the points of intersection for the tangent line and the circle. Our Z-min is 1.8 plus 2.4i, and Z-max is 4.2 plus 5.6i. The yellow one is the equation for the main circle. D is for the circle for Z-min, and E is the circle for Z-max. F is the tangent line for point A, and G is the tangent line for point B. Our mean argument is approximate 29.55 degree, and max argument is approximate 76.708 degree. These are the equations for the circles, points, lines, and argument angles.
Okay, next, let me go to the part B, the elliptical locus. On my part, I will describe the main proof of the algebra calculations. So first, the given locus is on the here, and we assume the Z1 is equal to 4 plus I, and Z2 is equal to 4 plus 9I, and A is equal to 10, and Z is equal to X plus Y. We substitute holding inside, and the X part will be the real number, and Y part will be the imaginary number, and we square and square root all the equations. Then we expand it and simplify it. After that, we square again, and we expand again and simplify again. And lastly, we use the complete the square method, and we divide whole the thing with the right side part, because the right side part should be 1, and the final answer A is equal to 3 and B is equal to 5.
Next, our goal is to find the maximum minimum modulus and argument for the complex number constrained by this elliptical equation. So we use geometry property that the extrema occur when the tangent is perpendicular to the radius vector. And by differentiating implicitly and solving for the intersection of these gradients, we will derive relationship between x and y. And by solving the relationship, it gives us 4 potential points. And by calculating their magnitude, we find the lowest and highest for the minimum and modulus. And moving on to the argument extrema, we look for the line passing through the origin that are tangent to ellipse. So we substitute y equals mx into the equation and set the discriminant into 0. And this to ensure that the ellipse touches exactly at one point. Lastly, by solving the quadratic for m, it gives us two slopes. The minimum argument occurs at the slope at 0 and corresponding to the real axis point, z equals to 4. The maximum argument occurs at the slope 40/7, which leads us to coordinate 1.17 plus 6.69i. This defines the angular boundaries of our complex region. Thank you.
Hi, my name is Khalif Pasha bin Titiwangsa, and I'm the GeoGebra architect for the ellipse part. We'll go straight into it. This is the ellipse equation derived by Mahayan Zhen, and then inserted here is this ellipse right here. And then what I did was I gathered a circle starting from the point D and then all the way to the point E, and take note of those equations right here, D and E respectively. And then from that, I've also gathered the Z max and then Z min values shown by H and I right here. And then I've also gathered the tangent equation, which is G and then A, using small letter G and then F respectively. So this is all the equations for reference. Using the GeoGebra's own function, we can actually cover the angle of argument minimum, and these are the ends for which the angle takes. So we got 30.527 for argument minimum, and then for maximum we got 62.34.
Now, let us see on the differences between the visual and the algebraic method. The visual method has lower precision compared to the algebraic method. The algebraic method provides exact values. As you can see here, the minimum argument is 29.55, while the minimum argument using the algebraic method is actually closer to 29.6. The visual method also provides quick insight, and the algebraic method is complex and time-consuming. Both methods have their own pros and cons. That is all for our video. Thank you for watching. Bye!